to algebra and power series. So the first thing we're going to take a look at is uniqueness of the coefficients. So we have a useful theorem which says that if the power series from n equals 0 to infinity, a sub n x minus x naught to the n is equal to the series from n equals 0 to infinity of b sub n times x minus x naught raised to the n on an open interval about x naught or containing x naught. So if we have two series representations that are essentially represent the exact same function on an open interval containing x naught, then an equals bn for all n. So in other words, the series are identical. Where this comes in handy, this means then that the Taylor series is the unique representation of a function. So the Taylor series of f about x naught is the unique power series in x minus x naught for f. It also gives us a trick for essentially solving for possible series that satisfies an equation. This gives us the ability to solve for a series that satisfies an equation. Or satisfies a specific equation. So that lends itself towards solving differential equations, with this ability to match coefficients and solve. Next up, we have linear combinations of power series. So essentially, we can condense linear combinations of power series in x minus x naught. So if we have C1 times the sum from n equals 0 to infinity of a sub n times x minus x naught to the n, and then plus C2 times the sum from n equals 0 to infinity of b sub n times x minus x naught to the n, then this is equal to the sum from n equals 0 to infinity of C1 times an plus C2 times bn, all times x minus x naught to the n. This will come in handy again if we're plugging in, say, derivatives of a series into a differential equation. We can combine and condense into one series and then again match coefficients. Another trick that will come in handy is what is called shifting the index of a power series. So if we have a power series the sum from n equals k to infinity of, say, a sub n times x minus x naught to the whatever. Oops, I apologize. I need to update my screen. So if we have a power series that starts at, say, n equals k going to infinity of a sub n times x minus x naught to, let's go with n minus k, we can go ahead and essentially do a shift and switch to a new variable. So let's set we can change to a new index. Typically, we want our index to be based off the power. So let's set j to be equal to n minus k. Then that means when n equals k, then j would equal 0. We have a sub n would be equal to a sub j plus k. And of course, n minus k is equal to j. So we get the sum from j equals 0 to infinity of a sub j plus k times x minus x naught to the j, or equivalently, we can swap j back for n now. We can index whoever we want in terms of the letter we use. So we can go from n equals 0 to infinity of a sub n plus k times x minus x naught to the n. So essentially, we're just taking our whole series, which has been originally indexed more by the coefficient than by the power. And now we're just shifting so that the power is our 0th term, or so that our first term is our 0th term again. So for an example, let's go ahead and use some linear combination and differentiation and index or re-indexing or shifting the index to try to simplify the expression 1 plus x in parentheses multiplying y double prime plus 3y prime minus 2y if y is equal to the sum from n equals 0 of an x to the n. So first thing we need, we have y is equal to the sum from n equals 0 to infinity of a sub n x to the n. We know y prime is the sum from n equals 1 to infinity of n times a sub n times x to the n minus 1. And we know the second derivative is equal to the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 2. So if we plug this into the equation, we wind up getting, we have 1 plus x in parentheses, multiplying the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 2. Then we have plus 3 times the sum from n equals 1 to infinity of n times a sub n times x to the n minus 1. And then we have minus 2 times the sum from n equals 0 to infinity of a sub n x to the n. So the first thing we want to do is just multiply in that 1 plus x. And we're going to do this just in two pieces. We'll multiply in the 1 and then multiply in the x. So this is all equal to, multiplying in 1, we just have the sum from n equals 2 to infinity of n times n minus 1, a sub n, x to the n minus 2. Multiplying in that n equals 2, the x, we would have plus the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 1. Multiplying in our 3, we have the sum from n equals 1 to infinity times 3 of 3n a sub n x to the n minus 1. And then we would have minus 2 or minus, let's just do plus the sum from n equals 0 to infinity of negative 2 a sub n x to the n. Now let's see what needs to be re-indexed. So if the power is not n, we need to re-index. So we have an n minus 2. So for this one, we're going to re-index by setting j equal to n minus 2. Then the middle two terms, we have an exponent of n minus 1. So we're going to re-index by setting, let's do k in this case, equal to n minus 1. And then the last one doesn't need re-indexing. So this is now equal to the sum from j equals 0 to infinity of, we would have j plus 2 times j plus 1 times a sub j plus 2 times x to the j for our first term. For our second term, we're going to actually start at k equals 1, since we're just doing a shift by 1, even though our n was starting at 2. So we'll go from k equals 1 to infinity. Now we'll have k plus 1 times k times a sub k plus 1 times x to the k. Let me update my screen one more time. Then that third term, again, we're just shifting by 1. This time around, we will start at k equals 0 to infinity. And then we have 3, n becomes k plus 1 times a sub k plus 1 times x to the k. And then our last one just stays the sum from n equals 0 to infinity of negative 2 a sub n x to the n. So at this stage, we are just re-indexing. Now it often gets confusing having the various different letters. We're allowed to use any letter we want for our index name. So let's just rename everything with n. So renaming, we can write this as the sum from n equals 0 to infinity of n plus 2 times n plus 1 times a sub n plus 2 times x to the n plus the sum from n equals 1 to infinity of n plus 1 times n times a sub n plus 1 times x to the n plus the sum from n equals 0 to infinity of 3 times n plus 1 times a sub n plus 1 times x to the n, and then plus the sum from n equals 0 to infinity of -2 times an times x to the n. At this point, you do have a choice. In this particular problem, the only term that starts with n equals 1, if we did start at n equals 0, we would just have 0 as our term since we have an n plus 1 times n. So if you wanted to, we could rewrite that as n equals 0 to infinity. The other option we have is simply to do the n equals 0 term on its own and then combine everything else. So we could do our n equals 0 term on its own. So the 0 term for that first one, we have 2 times 1, so 2 times a sub 2 times x to the 0th for that first term. The second term doesn't have an n equals 0. The third term, we would have 3 times 1, 0 plus 1 is 1, times a sub 1 times x to the 0th. And then our last term, we would have plus a -2 times a sub 0 times x to the 0th. And then beyond this, we will have the sum from n equals 1 to infinity of, we have n plus 2 times n plus 1 times a sub n plus 2. Then we have plus n plus 1 times n times a sub n plus 1. Then we have plus 3 times n plus 1 times a sub n plus 1. And then finally, -2 times a sub n. All of those combined should be the coefficient for x to the n. And then, of course, we could do more simplifying beyond that because we do have 2 a sub n plus 1s in there. But for the moment, we'll just leave it like this.